Okay, today's aim is understanding line symmetry, rotational symmetry, and point symmetry. So these are different types of symmetry we will find in geometry, and they're all pretty easy to understand once you understand the approach to distinguishing them. So the first one we're going to tackle is line symmetry. So let's first read the definition of line symmetry and then try to decipher what all these words mean. So the definition is a set of points has line symmetry if and only if there is a line L such that the reflection through L of each point of the set is also a point on the set. What do they mean by all that? Okay, well, let's see. This is a regular pentagon, as you can tell. This is actually a set of points that makes up a regular pentagon. What we're saying is as follows. Each one of these lines is made up of millions and millions and billions and billions of points. And what we're saying is this pentagon is a set of points that basically form this regular pentagon. And it says a set of points has line symmetry. In other words, this regular pentagon has line symmetry if and only if what? That there is a line L, such that the reflection through L of each point, in other words, each point, let's take point P, for example, each point, the reflection of each point through line L, and notice how there's a reflection through line L and it maps onto P prime. It says such that the reflection through L of each point of the set is also a point on the set. Now notice how P prime is a point on the set of points that make up this regular pentagon, and P is a point that is part of a set of points that makes up this regular pentagon. In other words, each point on this pentagon can be reflected over the line of symmetry and it will map to a point on the pentagon. This point over here, we'll call this A. This point A, when reflected over this line L, also maps onto the pentagon, A prime. If that's the case with every single one of these points, and it is the case with every single one of these points, if I took a point over here, I don't know, we'll call this B. If we reflect B across the line L, we'll get this point B prime, and we'll notice that these are the same. These lengths are the same. The distance from the pre-image and image to the line of reflection are the same. The same thing is here. The same thing is here. So this regular pentagon has line symmetry. Why? Because every point that is on this set of points, namely every point that is on this regular pentagon, can be reflected over this line of symmetry L, and where will I land? I will land on the pentagon. Okay, so let's find a more easily understandable definition of line symmetry. A figure has line symmetry if a line can be drawn through the figure so that the part of the figure on one side of the line is the mirror image of the part on the other side. Well, that's easy for us to understand. What we're saying is that in this triangle, every point on this side of the triangle, when reflected over this dashed line, will land on the triangle. This point over here, when reflected over this dashed line, will land on the triangle, and so forth all the way up the side of the triangle. Same thing here. Every point on this letter K, when reflected over this dashed line, will land on the letter K. Every point on this part of the letter K, when reflected over this line L, this dashed line, the line of symmetry, will land on the letter K. Remember, the length of the pre-image to the image is the same distance to the line of reflection. So the distance from the pre-image to the line of reflection and the distance from the image to the line of reflection is the same. And remember, you always are creating a right angle. The line connecting the pre-image to the image is perpendicular to the line of reflection. Same thing if you look over here. This is a diagonal line of reflection. This is a horizontal line of reflection. So every point on this quadrilateral, when reflected over this dashed line, will map to a point on the quadrilateral. In this case, I have a square. Every point on this part of the square, when reflected over this dashed diagonal line, will land on the square. In the case of a square, I have 4 lines of symmetry. Let's take a look at symmetry in nature. So here's an example of a line of symmetry that divides a butterfly in half. Notice how the two sides of the butterfly are symmetrical. Same thing with this beautiful orchid. Same thing with this this piece of artwork, and same thing with what looks like a caterpillar. And the same thing applies with this lovely bug. It is perfectly symmetrical. The line of symmetry is this vertical line that basically creates a mirror image of the left and right side of the bug. Same thing with this beetle over here. Let's take a look at some objects in geometry. So there are lines of symmetry in the alphabet. This A, for example, has a vertical line of symmetry. This letter B has a horizontal line of symmetry. This letter X, we could say, has both a vertical and horizontal line of symmetry. This word mom has a vertical line of symmetry. The word heat has a horizontal line of symmetry. I think you get the picture. Going back to geometry, if we take a square, for example, we saw before that a square has 4 lines of symmetry. 1 vertical, 1 horizontal, and 2 diagonal. An equilateral triangle has 3 lines of symmetry. One that goes through each one of the vertices and is perpendicular to the base of the triangle, as you can see right over here. A rectangle, on the other hand, only has a vertical and horizontal line of symmetry. Why is that? Well, if I decided to try to draw a diagonal line of symmetry, what would actually happen? Let's see. So a diagonal line of symmetry would look something like this, right? But is this really a line of symmetry? Remember, a line of symmetry must allow each point on the polygon to map to itself. So if I took, for example, this point over here, that is on my polygon, that is on the rectangle, and I wanted to reflect that point across the line of reflection, where would that map to? That would map to someplace over here, which is nowhere near the other part of my rectangle. So a rectangle only has vertical and horizontal line symmetry. It does not have diagonal line symmetry. Okay, let's take a look at some other cases. So it says, answer the following question in your groups. How many lines of symmetry do each of the regular polygons have? Remember, they are regular polygons. Okay, that's important. These are regular polygons, right? Which means that all sides are congruent. So how many lines of symmetry does a regular triangle have? Another word for a regular triangle, obviously, is an equilateral triangle. So how many lines of symmetry does this have? Well, let's see. Let's do this in let's make a dashed line, and let's do it in blue. Okay, so I've got, well, that doesn't look like a dashed line at all, does it? Let's try this again. And let's make it thin. There we go. Okay, so there's one line of symmetry. And let's see if we can find another line of symmetry. So we're going to draw another line of symmetry, and that will be like this. There's another line of symmetry. And finally, a third line of symmetry would be like this. So it looks like an equilateral triangle has 3 lines of symmetry. How about a square? So I first have this vertical line of symmetry. I then have this horizontal line of symmetry. So now I have 2. But then I also have this diagonal line of symmetry going from the upper right to the lower left, and finally from the upper left to the lower right. So I have 4 lines of symmetry. How about this regular pentagon? So let's see. I've got first this vertical line of symmetry, and then I have this diagonal line of symmetry, and you will notice that I can actually draw a line of symmetry through each of the vertices. And that's exactly what we are doing. We are drawing a line of symmetry through each of the vertices. So it looks like a regular pentagon has 5 lines of symmetry. And let's take a look at a regular hexagon. So again, I'm going to draw a line through the vertices. So there's 1, there's 2, there's 3. But am I done? No, I'm not done. I can actually draw a line of symmetry that goes through the top and the bottom bases of my regular hexagon. I can also draw another diagonal line of symmetry like this, and finally I can draw another line of symmetry like that. So let's actually count all these all together. So what do I have? Let's see. So I've got 1, 2, 3, 4, 5, 6. I don't want to count this again because that's part of line 1, this is part of line 2, this is part of line 3, etc. Let's see what I got here. I've got 1, 2, 3, 4, 5. We're doing the regular pentagon right now. I don't want to count this again because that's part of line 1. For the square, I've got 1, 2, 3, 4. I don't want to count this again because that's part of line 1. And here I've got 3. So it looks like my conjecture is that the number of lines of symmetry is equal to the number of sides of my regular polygon. So in other words, if I have the number of lines of symmetry of any regular polygon is equal to the number of vertices, or the number of sides. So how many lines of symmetry does an n-gon have? An n-gon has n lines of symmetry. In other words, I can draw as many lines of symmetry as I have sides to my regular polygon. Okay, let's take a look at this. How many lines of symmetry does an isosceles triangle have? Well, let's see. So again, we're going to try to draw lines of symmetry. And here we go. So let's draw a line of symmetry that goes through B. Now, can I draw a line of symmetry that goes through A? Well, let's see. If I drew a line that went through vertex A, well, that's kind of tough to do because already if I do something like this, point C, when reflected over this line, does not map to a point on my triangle. And this point over here, if I were to take a point, let's say right over here, for example, if I were to take this and reflect it over the line of symmetry, well, I end up being somewhere in the middle of my triangle, not on my triangle. So it looks like this isosceles triangle really only has one line of symmetry, and that is the line of symmetry from the vertex of my isosceles triangle. How about this scalene triangle? Can I draw a line of symmetry on this scalene triangle? In other words, is there line symmetry with this scalene triangle? And the answer is no, there is not. I mean, if I drew something like this, not every point on my triangle on line segment AC is going to map to a point on my triangle. So again, in this case, no, I do not have line symmetry. So this has no line symmetry, whereas this has one line symmetry. Okay, great. Let's take a look at another example. Determine the number of lines of symmetry of the following figures. We did something like this before. We noticed that yes, I have line symmetry for a vertical line with the rectangle. I have horizontal symmetry, but I do not have diagonal symmetry, because if I did try to draw a line that was diagonally across, every point on my rectangle would not map to a point that is still on my rectangle when I reflected it over this diagonal line. So we only have two lines of symmetry, horizontal and vertical, and that is all. And how about a square? We noticed that a square has four lines of symmetry. We saw that before. Next, let's talk about rotational symmetry. So a figure has rotational symmetry if there is a rotation of 180 degrees or less for which the figure maps is its own image, or maps onto itself. So for example, if I can take this equilateral triangle and I can rotate it a certain number of degrees and fit it on top of itself, then it has rotational symmetry. So let's see. Can I do that? Can I rotate this around and actually fit it onto the original figure? And yes, I can. I've just done it. Can I do it again? Let's see. Yes, I can do it again. And can I do it a third time? Well, if I do it a third time, I map right onto where I started, namely itself. There we go. So it says a figure has rotational symmetry if there is a rotation of 180 degrees or less for which the figure is its own image. The angle of rotation for rotational symmetry is the smallest angle needed for the figure to rotate onto itself. So how do I know what the angle of rotation is? Well, what I'm going to do is I know that a circle has 360 degrees. So I know, for example, that I have 360 degrees in a circle. And each of these central angles, each of these angles that is in the center of this circle, is going to be equal to each other because I've essentially created three congruent triangles. So I'm going to do is I'm going to divide 360 by 3, which is equal to 120. So each of these angles that is a central angle, is equal to 120. And you notice that I was able to rotate, so this is 120 degrees, and this is 120, and so is this 120. So I was able to rotate my triangle 120 degrees, and my triangle ABC mapped onto itself. So the rotational symmetry is 180 degrees rotational symmetry. The angle of rotation for rotational symmetry of this equilateral triangle is 120 degrees. If I rotate 120 degrees, if I rotate this figure 120 degrees, I'll map right on to myself. There we go. Okay. So let's take a look at another example. An object has rotational symmetry if there is a center point around which the object is turned or rotated a certain number of degrees and the object looks the same. And we saw that's exactly the case here. I rotated it 120 degrees, the object looks the same. So in this case, what I'm going to do is I'm going to take this regular pentagon and I'm going to rotate it a certain number of degrees, and it maps onto itself. I rotated it again a certain number of degrees, those same number of degrees, and again my regular pentagon maps onto itself. I'm going to do it a third time, and again the object maps onto itself. A fourth time, and the object maps onto itself, and finally a fifth time. So what is the angle of rotation going to be? So first of all, what is the point of rotation? Well, the point of rotation is going to be a point somewhere in the middle, right over here. That is the point of rotation. How do I find the angle of rotation? Well, let's see. I'm going to draw separate lines from the center to each of these vertices. Here we go. Not too shabby. I want to find the measure of each of these central angles, each of the angles that is created by the spoke of my wheel, so to speak, and the center. Well, what do I have? I have a regular pentagon, right? So I want to find the measure of each of these angles in here. So I'm going to take 360, because that's the number of degrees in a circle, and I'm going to divide it by 5, because that's the number of central angles I have, right? So if you divide 5 into 360, what do I have? I have 7 times 5, which is 35, and there we go, and the answer is 72. So each of these central angles is 72 degrees. Each of these is 72 degrees. So it looks like I have rotational symmetry. That's no question, because every 72 degrees you saw me before, I rotated at 72 degrees and I mapped onto my pentagon. What is the number of degrees of my rotation? In other words, the angle of rotation for rotational symmetry for this regular pentagon, the angle of rotation is 72 degrees. The angle of rotation is equal to 72 degrees. Now there's another thing here that is very curious. There's a word that says order, and it says the number of positions in which the object looks exactly the same is called the order of symmetry. So how many positions will this object look the same? Well, how many 72 degree rotations did I need to do for the object to look the same? Well, it looks like I needed to do 5, so the order is 5. The number of positions in which the object looks exactly the same is called the order of rotation. So the number of positions where this regular pentagon looks the same is 5, because I was able to do 5 72 degree rotations and the object does not change. When determining order, the last rotation returns the object to its original position, and we saw that. The last 72 degree rotation brought the A back onto itself, like that. Order 1 implies no rotational symmetry. Let's see what we mean. So, does this figure have rotational symmetry? Well, let's see. I'm going to try to rotate this a certain number of degrees, fewer than 360, and let's see if it maps onto itself. No, still not. Now finally did. But the thing is, the order was 1. So this really does not have rotational symmetry, because remember, order 1 implies no rotational symmetry since a full 360-degree rotation was needed, and that's exactly what was needed here. So the answer is no. Not like that. The answer is no. Let me see if I can write the word no. There we go. No. Or better yet, no, it does not have any rotational symmetry. Let's see if you can do these. So see if you can figure out the order for each of these polygons. Put your player on pause and hit play to resume when you are done. Okay, the order here would be 4, because I can rotate 90 degrees. Each 90-degree rotation will map the square onto itself. The order here would be 2, because the H rotated 180 degrees gives me one rotation of 180 degrees. Remember, for something to have rotational symmetry, it must rotate 180 degrees or less for there to be rotational symmetry. This is order 2. This would be order 3. I would have to rotate 120 degrees for one arrow to be mapped onto the next. And this has order 1, which means, is there rotational symmetry? No, there is no rotational symmetry. Very nice. See if you can figure out this one. So, what is the order for this figure? As you guessed it, the order is 2, because if I do a 180-degree rotation, my top triangle maps onto my bottom. This would be order 4. Every 90-degree rotation would map the figure onto itself. This would be order, well, let's see, we have to actually count the number of petals we have in this flower. So we got 1, 2, 3, 4, 5, 6, 7, 8. So it looks like the order is 8. Let's see if that's true. That is correct. What is this order? Well, let's see. If I rotated this 180 degrees, would the black part of the top sun map onto another black part of the sun? No, it would not. It would map onto a white part of the sun. So in this case, we do not have, this is order 1, because I would need to rotate 180 degrees for the black part of the top part of the sun to map onto itself, the black part of the top part of the sun. And therefore, there is no rotational symmetry. That is correct. Okay, that's it for line symmetry and rotational symmetry. I hope that helped.